right, now we're going to talk about signal spaces, that is, spaces of signals. So these are some example spaces of signals. We'll talk about Banach spaces and then some other types of signals. Banach spaces is a math definition, and it basically corresponds to what is called a complete linear vector space. So we've already seen what a vector space is. Vector space is, remember, closed, under, addition, scalar multiplication, those kinds of things. So we have those definitions for a linear vector space. So a Banach space is a vector space, but it's a vector space with a couple of other important properties. First important property is that a convergent sequence, for any convergent sequence, converges to an element in the space. So here's an example of a sequence of functions. So each of these functions, for example, here, notice each of these functions is bounded, and the sequence converges to a signal that's bounded. So in this case, this would be an example. If our signal space is the space of bounded signals, then this sequence converges to something in the space. If we were talking about signals that were continuous, okay, continuous means that they're connected. Okay, so notice that this signal and this signal are very similar. It's connected, but the limit, it becomes a square wave, which doesn't have isn't connected. So in that case, the space of continuous functions would not be a Banach space, because I can take a sequence of functions that get closer and closer to a step function, and the step function itself, however, is not a bounded sequence. It's not continuous, so that wouldn't work. So that's an example of a complete linear vector space. A sequence of functions converges to something in the space for a Banach space. So one important aspect of a Banach space is that it includes a norm. So a linear vector space didn't necessarily include a norm. You could have a normed vector space. So we've seen that before, but a vector space it's not required to have a norm. So in a Banach space, every element in the space has a finite norm value. Okay, so you don't have signals that are infinite, that have infinite norm value, that are in the space. So the classical Banach spaces are the little LP and the big LP spaces. So a discrete time signal is in little LP if and only if the P norm, so the discrete time P norm of that signal, is finite. It is in the continuous time, W is in the big LP, so little l corresponds to discrete, big L corresponds to continuous. So it's in the continuous LP space if the continuous time P norm of that signal is finite. So you can go through and show that these that these are spaces, and that they satisfy that they are a vector space. So notice we're not saying anything about continuous here. Okay, we're not saying differentiable. We're not saying anything like that. We're just saying that the P norm is finite. So clearly, if I have two signals, they both have finite P norm. Because we have a norm, then we have the triangle inequality, right? We have the triangle. So that is, if I sum those two elements, the sum of those two elements in norm is going to be less than or equal to the sum of the individual norms, but both of those are finite. Therefore, the sum is going to have finite norm. So it's going to also be in the space. And similarly with the scalar, because you have a norm defined, for any finite scalar, we can always show that scalar times the vector, the signal is still in finite norm. So the three important Banach spaces that we will use most of the time are the L1, L2, and L infinity spaces. Okay, so L1 is the space of finite available resource signals, or finite action signals. L2 is the space of finite energy signals, and L infinity is a space of bounded amplitude signals. Okay, so these are the most important of the Banach spaces. So the important thing is we not only have a signal but we also have a norm associated with it, and we know that if something is in that space, that it has finite norm, has a finite norm. Okay, so these are Banach spaces, and so these are the classical spaces. There are actually other Banach spaces. I'm not going to go into all that. Okay, we're going to stick with these. As far as other signal spaces, we have the space of power signals. So W is in the space of power signals if and only if its power is finite. The space of RMS signals. W is in the space of RMS signals if and only if its RMS value is finite. Okay, so these are not norm. So power is not a norm. The RMS is not a norm, and so you can go through and show that these measures do not constitute a valid norm, and so so as a result, they're not Banach. These are not Banach spaces, but they're still useful spaces because they have practical meaning. Okay, finite power, finite RMS value. Now, these spaces, there are actually relationships between the spaces. So if W is either in L1 or L2, then it is automatically in L infinity. That is, it's bounded in L infinity. Similarly, but if W is bounded in L infinity, that does not imply that W is either in L1 or L infinity. Okay. If W is a continuous time signal and W is in L2, that does not imply that W is bounded. If W is bounded, that does not imply that W is in L2. So finite energy does not mean it's bounded magnitude. Bounded magnitude does not imply that it is bounded energy. Okay, so you don't have those things. If W is in L infinity, either continuous time or discrete time, and the power exists, that is, it's finite, then the infinity norm is greater than or equal to the power. So we have this relationship. So some other aspects of the relationships. In discrete time, L infinity, we can think of it as the space. L2 is embedded within that. L1 is embedded within that, and there is some overlap between them. In terms of the big L, we have these relationships. That is, we have signals that are in L1 but not in L2 or L infinity. So that's what this illustrates. This illustrates the fact that there are signals in L2 that are not in L1 or L infinity, and then there are signals in L infinity that are not in L2 or L1, and we have signals that overlap. So, for example, here I would have signals that are in all three. Here I have signals that are in both L1 and L2, but not L infinity. And then this space is the space where I'm in L infinity and L2, but not L1. So we can have all those different kinds of things going on, and we'll look at some of those examples in our practice problems video. Stay tuned now for the Bibo theorem.